Okay, so we're starting on our second unit on probability paradoxes, and I want to start with a really famous paradox called Monty Hall paradox. So let's jump right in. Okay, so this is a famous paradox, so it's possible that some of you have seen it or heard of it, but it's really counterintuitive paradox. I hope you like it. So Monty Hall is a game show host of a show called Let's Make a Deal. Not the new rebooted version, but the old version of Let's Make a Deal. In the show, so this paradox is inspired by that show, and the contestants were given three doors, and one of the door hides a prize that they really want, let's say like a new car, and then the other two doors hid like a prize that they didn't want, like a goat or something. What happens is that you get to choose a door. So it could be the door with the car behind it or a goat behind it. But to make the show more exciting, what Monty Hall would do is to reveal one of the other doors that you didn't pick that have a goat behind it. So he eliminates one of the possibilities. Then, like, okay, all right, like, do you want to stick with your original decision, or would you like to switch your decision to the third door that hasn't been revealed yet? And this paradox is about that decision. So I think in the actual show, you weren't given a choice to switch the door later, but suppose they did. How would that go? So for this paradox, I think we can go to a website here, and to do this like interactively through a website. So let's jump to that website. Okay, so this is what the website looks like. So you are given three different doors, so you can pick one of the three. So I clicked on the third door, and Monty revealed the door number 2, which had a goat behind it. I can click on the 3 again, showing that I'm going to stick to my original choice. Or if I wanted to change my mind, I can click on door 1 instead. So I'm going to stick with my original choice this time. And then I was right to make that decision. So I got the car. And if I want to reset the show, I can click on play again, and I could do the same thing again. So maybe I'll click 1 this time. They reveal the door number 3 with the goat. When Monty knows where the car is, so he could always open a door with a goat that you haven't chosen. This time, let's switch the door, and I lost, right? So I should have stuck with the original decision. Okay, so what I want you to do is pause this video and try to do this. So it seems like maybe it doesn't matter whether you stick with the original decision or change it, because when there's two doors left, it seems like maybe 50-50 is the chance of winning or losing, and it shouldn't matter what you choose. But that's the surprising part. So try to pick a door and stick with the strategy of staying with the door and see what you get for 10 tries. So to try it out. And now switch up the strategy. So you can pick any of the three doors, but once the Monty reveals one of the wrong doors, I want you to switch and see how that goes. So I encourage you to pause the video and write out those 20 trials. After you're done, you could like come to a conclusion of which strategy worked out better for you, or did it not matter. And the website resets the statistics like every once in a while, but it does keep track of like how many people have won or lost using each strategy. So it's possible that your trial of like 20, 10 with each strategy might given you the wrong impression of what's actually better. It's random, so it could happen, right? Um, but overall statistics should show one of the strategy to work out better than the other. And then see if you can explain how that happened, right? So um, one way to do it is with a table. Okay, so there's three choices: door one, door two, and door three. And let's say strategy to switch or strategy to stay. Okay, so let's say just to make the things simpler, we always choose door one at first. Like if I chose door two or door three, just kind of relabel the door. So it's named one. And there's really three different possibilities of where the car could be. So car could be in the door one in the right place, or in door two or door three. And the other two doors has the wrong, like goats behind it. So let's work out what would happen if you chosen the right door. So if you chosen the right door, the Monty will reveal either two or the three. So they both have a go behind it. So he has a choice in this case, and maybe reveals that door. Whichever one he reveals, it doesn't matter because if you switched, you'd go to the goat. So this is the wrong decision. But if you've decided to stay, that would be the correct decision. Okay. Let's now consider the case where the car was behind door number two. Okay, so you still chose door number one at the first step. But if you've chosen this door and Monty has to reveal a goat, he's kind of forced to reveal the door number three because that's the only other door that has goat behind it. So Monty will reveal door three and say, oh, this is where the goat is. Would you like to switch or not? In this case, switching is the right decision because car is in behind door number two. So switching is the correct decision. And staying is the wrong decision. On the final possibility, you still chose door number one. Monty reveals door number two. So here again, switching is the correct decision. So you chose goat originally, and then the only other choice that's left over is the one with the car. So you would like to switch. Staying is the wrong choice. And now you might be able to see that we've listed out all possibilities in the case where you chose door number one. And you would be making the correct decision 2/3 of the time. And if you stuck with the staying strategy, you'd be only correct 1/3 at a time. It's not really 50-50. Even though there are two choices, it's more likely to be in the other door because the other wrong decision has been eliminated for you already. So it's more likely that the leftover door is the one with the car. I hope that made sense. And I hope you come to a conclusion that determining these probabilities are difficult to work out. It really, a lot of people's gut feelings tell them that it should be 50-50 in this case, and that's wrong. So I would like to cover some basic probability theory in this unit. And we'll cover different types of unintuitive like paradoxes. But for this video, I think I want to at least get to like a common terminology of what probability is. So I am going to jump to notes here. So some basic terminology. So when we say probability, probability is a branch of mathematics used to analyze experiments where outcome is uncertain or it's not predetermined. So here's some definitions. So the set of all possible outcomes in a random experiment is called sample space. So this is the universe of the probability, all possible outcomes. So, I mean, that depends on the random experiment you're running. So for example, if you just do a coin flip and you can get heads or tails, then sample space is just those two elements. You either get heads or you get tails. If you roll a six-sided die, you get one of these 6 possible outcomes. Your sample space does not have to be finite. For example, if you're flipping a coin until you get your first heads, you could get heads right away, or you could get tails and heads, tails, then heads, tails, then heads, and so on. So you could get any number of tails before you actually get your first head. So if you're writing out all possibilities, there's infinitely many of them. So sample space could be infinite. Another sample space could be with a random experiment of taking a stopwatch and measuring time until the next bus arrival. Time could be 0, the bus could come right away, or it could take any number of minutes. Maybe the bus gets in a car crash and the bus stop gets changed and your bus stop gets eliminated, maybe it never comes. But it could be any 0 off until any number of minutes. So any positive number will do in this case. Okay, so that's the sample space. So sample space is all possible outcomes. An event is any subset of the sample space. So in the previous 4 situations, you could talk about an event of getting heads instead of tails. So that's a subset of the entire sample space, so that counts as an event. Maybe you're looking at an event of rolling an even number on a 6-sided die, or maybe an event of flipping heads within the first 3 flips. Or maybe like a bus arrives within the first 5 minutes. So all of these are subset of the sample space, so it's considered an event. I should also note that empty event counts as well. So subset of nothing counts as an event, and also subset of everything counts as an event as well. So the entire sample space itself counts as an event. Okay. All right. So we haven't talked about probability yet, right? So these are possibilities and subsets of possibilities. So probability is an actual number that you assign to an event that's anywhere between 0 and 1. So if you call something a probability measure, there's 3 conditions. So the first condition is that for any event A, the probability is somewhere between 0 and 1. So it could be 0, it could be 1, or it could be anywhere in between, but it can't be negative, and you can't have a probability that's greater than 1. So if you're computing probabilities and getting 1.2 is an answer, you know you're doing something wrong. The second condition is actually pretty straightforward. If you add up the probability for every possibility, so the probability of the sample space, probability of something in the sample space happening is equal to 1. So that's saying that something will happen when you run this experiment. And one more requirement on how these probabilities work. If you have two events A and B that are mutually exclusive, so that's a fancy way of saying the two events have nothing in intersection. So you can't have A and B happen at the same time. Then if you have mutually exclusive events, then the probabilities add. So probability that one or the other happens is the sum of the two possible two events separately. Okay, so these are the three conditions that you have to satisfy before you can call something a probability. We're gonna work on how to compute these things with future videos, but those are the three words that I want you to know: sample space, event, and the probability measure. Okay, that's it for today. I'll see you guys Friday. Bye.